So this is the second video dealing with the main organic reactions, and we're only going to look at two here, and we'll look at one fairly extensively, but we're looking at oxidation reduction reactions. Now you may just want to pause the video for a minute or two and just have a read of what's written here, and then I'll sort of go through and highlight a few important bits. So oxidation reduction in organic chemistry is unlike how the same process is dealt with in electrochemistry. We'll do that later in the year. In electrochem, we look at electron transfer, and essentially what we see is a reactant being oxidized and at the same time a reactant being reduced. This is why they're known as redox reactions. In organic chem, we focus in on the organic reactant only, and we look at oxidation as a process that takes place in the reactant, or we look at reduction as something that happens to the reactant. And when we look at this from the organic context, we're looking at oxidation and reduction as showing up as changes in bonding in the carbon atoms, and specifically changes in bonding to oxygen, or so increased bonding of oxygen or a decreased bonding of oxygen. And we can look at the same context in terms of hydrogen. But we can also classify these as in terms of reactions we're already familiar with. So when we form a C-double bond, we've seen formation of a multiple or double bond as an elimination reaction. And so oxidation can sometimes be looked at as elimination, and a reduction on the other hand is the same as addition reaction. So we can add hydrogens to a double bond, and that then looks a lot like an addition reaction. So let's look at oxidation first. So oxidation in organic chemistry is described as a reaction with carbon atoms for more bonds to oxygen. And so when we control this, we can produce aldehydes and ketones from alcohols, and in so doing we convert the hydroxyl group, the COH group, into a carbonyl group. And so you can see C single bond O to C double bond O, more bonds to oxygen, and in so doing fewer bonds to hydrogen. And common oxidizing agent, and you should remember these, try to remember these: potassium permanganate, it's really the permanganate ion that's of interest there, MnO4 minus. Potassium dichromate, again it's the dichromate ion, this is the strong oxidizer. And ozone is also an oxidizing agent, although that's more atmospheric than in the lab. So permanganate and dichromate ions, good oxidizers. So here's a common example. An alcohol, as I already mentioned, can be oxidized to yield a ketone or an aldehyde. So here we look at the aldehyde. So there's my aldehyde group, an ROH group, or sorry, my alcohol with an OH group. And if that's a terminal alcohol group, so that's a primary alcohol, it will be oxidized to yield an aldehyde. And so there's my carbonyl group. Just so you know, that brackets O represents the oxidizing agent. And so here's an example. Here's my primary alcohol. That alcohol would be called pentan 1-ol, because the OH group is on a terminal carbon, carbon 1. And if in the presence of an oxidizing agent and the correct conditions, I allow an oxidation to take place, I'm going to form an aldehyde. So on the same carbon, I now have a carbonyl group, C double bond O bond H. And so that's a very straightforward, typical oxidation of a primary alcohol. Okay, ketones also then are oxidized. So here's my secondary alcohol, and it gets oxidized to a ketone. So there's my C double bond O carbonyl group within the chain. So secondary alcohols get oxidized to ketones. So this is pentan pentane-2-ol, and pentane-2-ol then gets oxidized to pentane-2-one, a ketone. So secondary alcohol with the functional group on a carbon within the chain gives rise to a ketone. I guess I should maybe draw that ketone, eh? So that's going to be that. And so a secondary alcohol with a functional group on carbon 2 gives rise to a ketone with a carbonyl group in the same position, carbon 2. Now, further oxidation aldehydes. An aldehyde can be further oxidized, and if you look at the functional group we have now, there's my carbonyl group of an aldehyde. Well, there's the carbonyl group, and here's the increased carbon-oxygen bonding. So the addition of a hydroxyl group. And so aldehydes can be further oxidized to yield carboxylic acids. So in my example here, again, presence of an oxidizing agent, I take my, this is butanal, so I'm going to add there's my carbonyl group of butanal, and now I add the hydroxyl group OH, and so I produce butanoic acid. So aldehyde gets oxidized to a carboxylic acid. Now, one thing you want to be able to do is control the product, control the yield of the product. So as I've just pointed out, aldehydes can be oxidized from a, or produced from the oxidation of a primary alcohol. But if you leave that aldehyde in the reaction mixture, it's going to be further oxidized to yield carboxylic acid. But what if all you want is an aldehyde? You don't want any carboxylic acid. How are you going to control this? What if you want carboxylic acid? You want to make sure all of the aldehyde gets oxidized. How are you going to do that? Well, there's a couple of pretty standard techniques that nicely do this for us, both of them. So the process of distillation uses the heat and the different boiling points of a mixture, and then the condensation of a vapor to nicely separate out these things. So if we look at the process here, first thing we look at is our mixture. In our reaction vessel we have a mixture, and that is an alcohol with an oxidizing agent. And we don't have a huge amount of excess oxidizing agent. We want to make sure we have enough, but we don't want to have tons of it. We heat it. The heating causes the reaction to proceed fairly rapidly, for one thing, but it also, continued heating allows the aldehyde that gets formed to boil. And by boiling, we mean going from the liquid to the vapor state. And this it does before the alcohol, because the intermolecular forces in an aldehyde are just dipole-dipole forces, which are weaker than the hydrogen bonds in the alcohol. So the aldehyde boils first, vaporizes. So when we have a vapor, aldehyde vapor, it goes through this water jacketing, this condenser, which is typically cold water going through here, causes the vapor to condense. And when it condenses, it flows as a liquid into another vessel, and in that vessel we have our fairly pure aldehyde. And so distillation nicely separates out the aldehyde from the alcohol, and the alcohol will continue to react with oxidizing agent, but the aldehyde gets separated out. So if we want to separate it and maximize yield of aldehyde, we use distillation. Well, what if we want to maximize or make sure we oxidize all our aldehyde? Well, it's a different apparatus. This is known as a reflux apparatus. And so again, our mixture in the reaction vessel is an alcohol with excess oxidizing agent. So we want to make sure we have lots of extra oxidizing agent because we want to maximize the oxidation. So the heating, like before, drives the reaction, and again the aldehyde will boil before the alcohol and it vaporizes. But now the condenser doesn't have an outlet. The condenser is just basically a long high tube that's sealed at the top, but the aldehyde still condenses. But it condenses and falls back into the reaction mixture, falls back into the boiling flask, where there's excess oxidizing agent. And so back in the boiling flask, the aldehyde can be oxidized, and it gets oxidized into a carboxylic acid. And the carboxylic acid has the highest boiling point of anything, so it's just going to sit there, basically. And the aldehyde keeps boiling off, recondensing, and it gets oxidized. So eventually, the hope is you have pretty much mostly carboxylic acid. So reflux allows you to maximize the yield of a carboxylic acid. Now, further oxidation is not always possible, and here's the reason why. So we talked about an aldehyde being further oxidized. Well, here's a ketone. So this is my butanone, and butanone, what butanone doesn't have, I'm just quickly going to draw butanal. So here's butanal. And what butanal has that butanone doesn't have is that red hydrogen I've just drawn. So this hydrogen attached to the carbonyl group allows an aldehyde to get oxidized. All the alcohol's at it, and the aldehyde has this hydrogen attached to the carbonyl group, but the ketone doesn't. So the ketone does not get oxidized. So you can have all the oxidizing agent you want, but a ketone will not react. You'll get no further oxidation. And a carboxylic acid of this is the same. So this is a carboxylic acid. Carboxylic acids are not further oxidized. So the reaction stops with a ketone. Reaction stops with a carboxylic acid. Now, the other reaction that we want to look at is a reduction. And again, a reduction reaction, basically the opposite of oxidation, a reaction in which carbon adds for fewer bonds to oxygen. So aldehydes, ketones, and carboxylic acids, well, if they can be produced by oxidation, they can be reduced as well, and they get reduced to alcohols, not surprising, but you can also get them reduced to alkenes and alkynes. Common reducing agents, lithium aluminum hydride, basically a lithium complex cation, and hydrogen gas with a platinum catalyst. That's probably a bit more common because it actually produces quite a rapid reaction. And so reduction involving transformation of C double bond O or C double bond C bonds can be classified as an addition reaction, and you'll see that in a minute. So here's a few examples. Again, aldehyde or a ketone. So here's my ketone. Again, I'm back to butanone. Here's my reducing agent. So brackets H just as a generic reducing agent. And so if I'm reducing that, what am I going to get? Well, I reduce the amount of bonding to oxygen. So there it is. I have a single bond, O. And so that is going to be a hydroxyl group. And I have my two hydrogens attached to carbon 1, and the rest is saturated. So I get from butanone, sorry. Whoops, I put the OH on the wrong carbon. Let's go back and fix that. It's on carbon 2 because it stays, the oxygen stays on the same carbon. And so a ketone with that interior carbonyl group gives rise to a secondary alcohol. So that's going to be butane 2-ol. So ketone reduced to a secondary alcohol. So obviously an aldehyde would be reduced to a primary alcohol. And so it's simply, you can really look at it as the opposite of oxidation. Now, use of a hydrogen gas platinum catalyst as a reducing agent means you can look at this as an addition reaction called a hydrogenation, but again it looks a lot like an addition reaction because it's the addition of hydrogen. So here's my hydrogen, I'm going to add it to my C double bond O. So if I add that to C double bond O, here's my H, I'm going to add a hydrogen to that O, less bonding to the hydrogen, but I also then have room for another H. So there's the second H of the H2. So one of them to the OH, one of them to the carbon. And the rest are the same. And I get my organic product of that reduction, and that is going to be a primary alcohol. So this aldehyde, propanal, gets reduced to propanol, 1 propan, 1 ol. So propanone in the same reaction would be reduced to propan 2 ol. And that concludes this video.